Viviani gathered together his master's work, editing the first collected edition in 1655-56. Viviani's research included work on the speed of sound, which he measured to within 82 feet per second of its true value. He is best known, however, for his triangle theorem, which states that the sum of the distances between any point in an equilateral triangle and that triangle's sides is equal to the altitude of the triangle. Proving the theorem. Starting with an equilateral triangle of base A and an altitude of h, a point is made inside the triangle. Perpendicular lines are drawn from that point to each of the three sides, meeting each side at 90 degrees. The triangle is divided into three smaller triangles by drawing a line from the point to each corner of the main triangle. The area of a triangle is base height, so if the lengths of the perpendiculars are P, Q, and R, the areas of the triangles add up to A. This is also the area of the large triangle, which is Ha, and so H equals P plus Q plus R. If you were to break a stick of length H into three, there would always be a point in the triangle from which the pieces form the perpendiculars P, Q, and R. The altitude in an equilateral triangle, such as the above, is always equal to the combined length of lines drawn from any point in the triangle perpendicular to its three sides. See also Pythagoras, Euclid's Elements, Trigonometry, Projective Geometry, Non-Euclidean Geometries. In context. Key figure. Christian Huygens Field Geometry before 1503 French mathematician Charles de Bavels is the first to describe a cycloid. 1602 Galileo discovers that the time taken for a pendulum to complete a swing does not depend on the swing's width. After 1690 Swiss mathematician Jacob Bernoulli draws on Huygens's imperfect solution to the Tautochron problem to solve the brachistochrone problem, finding a curve of the fastest descent. Early 1700s the longitude problem is resolved by British clockmaker John Harrison and others, using springs rather than pendulums. In 1656, Dutch physicist and mathematician Christian Huygens created the pendulum clock, a clock with a swinging weight that was constant. He wanted to resolve the navigational problem of determining a ship's longitude. This was impossible without precise calculations of time, so it required an accurate clock to cope with the rolling motion of the waves, which caused wide variations in pendulum swing, leading to time discrepancies. Seeking the right curve. The key lay in finding a curved path for the pendulum to follow, whereby the time the pendulum takes to return to its lowest point is constant whatever its highest point. Huygens identified the cycloid, a curve that was steep at the top and shallow at the bottom. The curved path of any pendulum would have to be adjusted so it traveled in a cycloid. Huygens's idea was to constrain the pendulum by adding cycloid-shaped cheeks. In theory, the time of each movement would now be the same from any starting point. However, friction introduced a larger error than the one Huygens was trying to resolve. It was only in the 1750s that the Italian Joseph Louis Lagrange arrived at a solution, where the height of the curve needs to be in proportion to the square of the length of the arc traveled by the pendulum. I was struck by the remarkable fact that in geometry all bodies gliding along the cycloid descend from any point in precisely the same time. Herman Melville Moby Dick. See also, the area under a cyclopascal's triangle, the law of large numbers. In context. Key figures. Isaac Newton, Gottfried Leibniz Field Calculus before 287, 212 BC Archimedes uses the method of exhaustion to calculate areas and volumes, introducing the concept of infinitesimals. Circa 1630 Pierre de Fermat uses a new technique for finding tangents to curves, locating their maximum and minimum points. After 1740 Leonhard Euler applies the ideas of calculus to synthesize calculus, complex algebra, and trigonometry. 1823 French mathematician Augustin Louis Cauchy formalizes the fundamental theorem of calculus. The development of calculus, the branch of mathematics that deals with how things change, was one of the most significant advances in the history of mathematics. Calculus can show how the position of a moving vehicle changes over time, how the brightness of a light source dims as it moves further away, or how the position of a person's eyes alters as they follow a moving object. It can ascertain where changing phenomena reach a maximum or minimum value, and at what rate they travel between the two. Alongside rates of change, another important aspect of calculus is summation, which developed from the need to calculate areas. Eventually, the study of areas and volumes was formalized into what became known as integration, while calculating rates of change was termed differentiation. By providing a better understanding of the behavior of phenomena, calculus can be used to predict and influence their future state. In much the same way as algebra and arithmetic are tools for working with numerical or generalized quantities, calculus has its own rules, notations, and applications, and its development between the 17th and 19th centuries led to rapid progress in fields such as engineering and physics. Nothing takes place in the world whose meaning is not that of some maximum or minimum. Leonard Euler. Ancient origins. The ancient Babylonians and Egyptians were particularly interested in measurement. It was important for them to be able to calculate the dimensions of fields for growing and irrigating crops, and to work out the volume of buildings to store grain. They developed early notions of area and volume, although these tended to be in the form of very specific examples, such as in the Rhind Papyrus, where one problem involves the area of a round field with a diameter of 9 kth. The rules laid down in the Rhind Papyrus led ultimately to what would become known more than 3,000 years later as integral calculus. The concept of infinity is central to calculus. In ancient Greece, Zeno's paradoxes of motion, a set of philosophical problems devised by the philosopher Zeno of Elea in the 5th century BC, posited that motion was impossible because there are an infinite number of halfway points in any given distance. In around 370 BC, the Greek mathematician Eudoxus of Cnidus proposed a method of calculating the area of a shape by filling it with identical polygons of known area, and then making the polygons infinitely smaller. It was thought that their combined area would eventually converge toward the true area of the shape. This so-called method of exhaustion was taken up by Archimedes in around 225 BC. He approximated the area of a circle by enclosing it within polygons with increasing numbers of sides. As the number of sides increases, the polygons more closely resemble the circle. Taking this idea to the limit, Archimedes imagined a polygon with sides of infinitesimally smaller length. The recognition of infinitesimals was a pivotal moment in the development of calculus. Previously insoluble puzzles, such as Zeno's paradoxes of motion, could now be solved. For by the ultimate velocity is meant that, with which the body is moved, either before it arrives at its last place, when the motion ceases, nor after but at the very instant when it arrives. Isaac Newton. As civilizations developed, accurate measurement became essential. This ancient Egyptian tomb painting shows surveyors using rope to calculate the dimensions of a wheat field. Fresh ideas. Mathematicians in medieval China and India made further advances in dealing with infinite sums. In the Islamic world, too, the development of algebra meant that, rather than spelling out a calculation millions of times for all possible variations, generalized symbols could be used to prove that a case is true for all numbers to infinity. Mathematics had suffered a long period of stagnation in Europe, but, as the Renaissance took hold in the 1300s, renewed interest in the subject led to fresh ideas about motion and the laws governing distance and speed. French mathematician and philosopher Nicole Oersma studied the velocity of an accelerating object against time, and he realized that the area under a graph depicting this relationship was equivalent to the distance traveled by the object. This notion would be formalized in the late 1600s by Isaac Newton and Isaac Barrow in England, Gottfried Leibniz in Germany, and Scottish mathematician James Gregory. Oersma's work was inspired by that of the Oxford calculators, a 14th-century group of scholars based at Merton College, Oxford, who developed the mean speed theorem, which Oersma later proved. It states that if one body is moving with a uniformly accelerated motion and a second body is moving with a uniform speed equal to the mean speed of the first body, and both bodies are moving for the same duration, they will cover the same distance. The Merton scholars were devoted to solving physical and philosophical problems using calculations and logic, and were interested in the quantitative analysis of phenomena such as heat, color, light, and velocity. They were inspired by the trigonometry of Arab astronomer al-Battani and the logic and physics of Aristotle. This illustration of Kepler's Platonic solid model of the solar system appeared in a book published in 1596. Kepler used infinitesimally small strips to measure the distance covered in an orbit. This method was the forerunner of integration. New developments. The incremental steps toward the development of calculus gathered pace toward the end of the 16th century. In around 1600, French mathematician François Vite promoted the use of symbols in algebra, while Flemish mathematician Simon Stevin initiated the concept of mathematical limits, whereby the sum of amounts could converge to a limiting value, much like the area of Archimedes' polygons converged to the area of a circle. At much the same time, German mathematician and astronomer Johannes Kepler was researching the motion of the planets, including calculating the area enclosed by a planetary orbit, which he recognized as elliptical rather than circular. Using ancient Greek methods, he worked out the area by dividing the ellipse into strips of infinitesimal width. A forerunner of the more formal integration to come, Kepler's method was further developed in 1635 by Italian mathematician Bonaventura Cavalieri in Geometria Indivisibilibus Continuorum Nova Quadam Ration Promota. Cavalieri worked out a method of indivisibles, which was a more rigorous method of determining the size of shapes. More developments followed in the 1600s with the work of English theologian and mathematician Isaac Barrow and Italian physicist Evangelista Torricelli, followed by that of Pierre de Fermat and René Descartes, whose analysis of curves advanced the new area of graphical algebra. Fermat also located maxima and minima, the greatest and least values of a curve. Flux-ion model. In 1665-66, English mathematician Isaac Newton developed his method of flux ions, a method for calculating variables that changed over time, which was a milestone in the history of calculus. Like Kepler and Galileo, Newton was interested in studying moving bodies and was particularly eager to unify the laws governing the motion of celestial bodies with motion on Earth. In Newton's flux-ion model, he considered a point moving along a curve as being divided into two perpendicular components, and then considered the velocities of those components. This work laid the foundation for what became known as differential calculus, which together with the related field of integral calculus led to the fundamental theorem of calculus. The idea of differential calculus is that the rate at which a variable changes at a point is equal to the gradient of a tangent at that point. This can be pictured by drawing a tangent. The gradient or steepness of this line will be the rate of change of the curve at that point. Newton recognized that at the maxima and minima, the gradient of the curve was zero, because when something is at its highest or lowest point, it is momentarily not changing. Newton went on to develop his theory further by considering the converse problem. If the rate at which a variable changes is known, is it possible to calculate the shape of the variable itself? This anti-differentiation entailed working out areas under the curve. Differentiation can be used to find the rate of change at a given point in time. The blue line shows the rate of change overall, and the orange tangent shows the rate of change at a given point. The fundamental theorem of calculus. The study of calculus is underpinned by the fundamental theorem of calculus, specifying the relationship between differentiation and integration, both of which rely on the concept of infinitesimals. First articulated by James Gregory in his 1668 Geometrie pars universalis. It was then generalized by Isaac Barrow in 1670, and formalized in 1823 by Augustin Louis Cauchy. The theorem has two parts. The first states that integration and differentiation are opposites. For any continuous function, there exists an Antiderivative, whose derivative is the function itself. The second part of the theorem states that if values are inserted into the antiderivative f, the result, the definite integral of the function f, makes it possible to calculate areas under the curve of the function f. Newton v. Leibniz. Around the time that Newton was developing his calculus, German mathematician Gottfried Leibniz was working on his own version, based on the consideration of infinitesimal changes in the two coordinates defining a point on a curve. Leibniz used very different notation from Newton's, and in 1684 published a paper on what would later become known as differential calculus. 2 years later, he published another paper, this time about integration, again using different notation from that of Newton in an unpublished manuscript dated October 29, 1675. Leibniz was the first person to use the integral symbol, which is used and recognized universally today. There was much debate about who discovered modern calculus first, Newton or Leibniz. It led to protracted bitterness between the two rivals and across much of the mathematical community. Although Newton devised his theory of flux science in 1665-66, he did not publish it until 1704, when it was added as an appendix to his work Optics. Leibniz began to devise his version of calculus around 1673, and published it in 1684. Newton's subsequent Principia is said by some to have been influenced by Leibniz's work. By 1712, Leibniz and Newton were openly accusing one another of plagiarism. The modern consensus is that Leibniz and Newton developed their ideas on the subject independently. Significant contributions to calculus were also made in Switzerland by the brothers Jacob and Johann Bernoulli, who coined the term integral in 1690. Scottish mathematician Colin Maclaurin published his treatise on flux science in 1742, promoting and furthering Newton's methods, and attempting to make them more rigorous. In this work, Maclaurin applies calculus to the study of infinite series of algebraic terms. Meanwhile, Swiss mathematician James Gregory was the first person to formulate the fundamental theorem of calculus. Leonhard Euler, a close friend of Johann Bernoulli's sons, was influenced by their ideas on the subject. In particular, he applied the idea of infinitesimals to what is known as the exponential function, e. This ultimately led to Euler's identity. E plus 1 is equal to 0, an equation that connects 5 of the most fundamental mathematical quantities in a very simple way. As the 18th century progressed, calculus proved increasingly useful as a tool for describing and understanding the physical world. In the 1750s, Euler, working in collaboration with French mathematician Joseph-Louis Lagrange, used calculus to provide an equation, the Euler-Lagrange equation, for understanding both fluid and solid mechanics. In the early 1800s, French physicist and mathematician Pierre-Simon Laplace developed electromagnetic theory with the help of calculus. Assuming I know our instantaneous speed at every possible moment, can I then use that information to determine how far we've traveled? Calculus says I can. Jennifer Willett, American science writer. Isaac Newton's Optics, a treatise about the reflections and refractions of light, published in 1704, contains the first details of his work in the area of calculus. When the values successively assigned to the same variable indefinitely approach a fixed value, so as to end by differing from it as little as desired, this fixed value is called the limit. Augustin Louis Cauchy. Formalizing the theories. The various developments in calculus were formalized in 1823 when Augustin Louis Cauchy formally stated the fundamental theorem of calculus. In essence, this states that the process of differentiation is the inverse of the process of integration. Cauchy's formalization allowed calculus to be regarded as a unified whole, dealing with infinitesimals in a consistent way using universally agreed notation. The field of calculus was further developed later in the 1800s. In 1854, German mathematician Bernhard Riemann formulated criteria for which functions would be integrable or not, based on defining finite upper and lower limits for the function. Invented by Newton for differentiation. Invented by Leibniz for integration. dy dx. Invented by Leibniz for differentiation. F. Invented by Lagrange for differentiation. Ubiquitous applications. Many advances in physics and engineering have relied on calculus. Albert Einstein used it in his theories of special and general relativity in the early 20th century, and it has been applied extensively in quantum mechanics. Schrödinger's wave equation, a differential equation published in 1925 by Austrian physicist Erwin Schrödinger, models a particle as a wave whose state can only be determined by using probability. This was groundbreaking in a scientific world that had up until then been governed by certainty. Calculus has many important applications today. It is used, for instance, in search engines, construction projects, medical advances, economic models, and weather forecasts. It is difficult to imagine a world without this all-pervasive branch of mathematics, as it would most certainly be one without computers. Many would argue that calculus is the most important mathematical discovery in the last 400 years. Gottfried Leibniz. Born in Leipzig, Germany, in 1646, Gottfried Leibniz was raised in an academic family. His father was a professor of moral philosophy, while his mother was the daughter of a professor of law. In 1667, after completing his university studies, Leibniz became an advisor on law and politics to the Elector of Mainz, a role that enabled him to travel and meet other European scholars. After his employer's death in 1673, he took up the role of librarian to the Duke of Brunswick in Hanover. Leibniz was a celebrated philosopher as well as a mathematician. He never married and died in 1716 to little fanfare. His successes had been overshadowed by his calculus dispute with Newton, and were only recognized several years after his death. Key works: 1666 On the Art of Combination. 1684 New Method for Maximums and Minimums. 1703 Explanation of Binary Arithmetic. See also, the Rhine Papyrus Zeno's Paradoxes of Motion Calculating Pi Decimals. The Problem of Maxima. The Area under a Cycloid. Euler's Number. Euler's Identity. In context. Key figure: Gottfried Leibniz Fields. Number theory, logic before. Circa 2000 BC, ancient Egyptians use a binary system of doubling and having to carry out multiplication and division. Circa 1600, English mathematician and astrologer Thomas Harriot experiments with number systems, including binary. After 1854, George Boole uses binary arithmetic to develop Boolean algebra. 1937, Claude Shannon shows how Boolean algebra could be implemented using electronic circuits and binary code. 1998, 16-bit binary code is used to code pixels on a computer screen, allowing it to display more than 65,000 colors. In everyday life, we are used to the base 10 counting system with its familiar 10 digits, 0 to 9. When we count from 10 onward, we put a 1 in the tens column and a 0 in the units column, and so on, adding columns for hundreds, thousands, and beyond. The binary system is a base 2 counting system and employs just two symbols, 0 and 1. Rather than increasing in multiples of 10, each column represents a power of 2. So the binary number 1011 is not 1011 but 11. Binary choices are black and white. In any column there's only ever 1 or 0. This simple on or off concept has proved vital in computing, for example, where every number can be represented by a series of switch-like on-off actions. Binary numbers are written as ones and zeros, using a base 2 system. This chart shows how to write the numbers 1 to 10 from the base 10 system, as both binary numbers and binary visuals, which is how a computer would process them, where 1 is on and 0 is off. Binary power revealed. In 1617, Scottish mathematician John Napier announced a binary calculator based on a chessboard. Each square had a value, and that square's value was on or off, depending on whether a counter was placed on the square. The calculator could multiply, divide, and even find square roots, but was considered a mere curiosity. Around the same time, Thomas Harriot was experimenting with number systems, including the binary system. He was able to convert base 10 numbers to binary and back again, and could also calculate using binary numbers. However, Harriot's ideas remained unpublished until long after his death in 1621. The potential of binary numbers was finally realized by German mathematician and philosopher Gottfried Leibniz. In 1679, he described a calculating machine that worked on binary principles, with open or closed gates to let marbles fall through. Computers work in a similar way, using switches and electricity rather than gates and marbles. Leibniz outlined his ideas on the binary system in 1703 in Explanation of Binary Arithmetic, showing how zeros and ones could represent numbers and so simplify even the most complex operations into a basic binary form. He had been influenced by correspondence with missionaries in China, who introduced him to the I Ching, an ancient Chinese book of divination. The book divided reality into the two opposing poles of yin and yang, one represented as a broken line, the other as an unbroken line. These lines were displayed as 6-line hexagrams, combined into a total of 64 different patterns. Leibniz saw links between this binary approach to divination and his work with binary numbers. Above all, Leibniz was driven by his religious faith. He wanted to use logic to answer questions about God's existence and believed that the binary system captured his view of the universe's creation, with 0 representing nothingness and 1 representing God. Reckoning by twos, that is, by 0 and 1, is the most fundamental way of reckoning for science, and offers up new discoveries, which are useful, even for the practice of numbers. Gottfried Leibniz. The teaching and commentaries on the I Ching of ancient Chinese philosopher Confucius influenced the work of Leibniz and other 17th, 18th century scientists. Bacon's cipher. English philosopher and courtier Francis Bacon was a great dabbler in cryptography, or the science of deciphering codes. He developed what he called a biliteral cipher, which used the letters A and B to generate the entire alphabet: A equals AAA, B equals AUB, C equals ABA, D equals AAB, and so on. If you substitute 0 for A and 1 for B, this becomes a binary sequence. It is an easy code to break, but Bacon realized that A and B do not have to be letters, they can be any two different objects, as by bells, by trumpets, by lights and torches, and any instruments of like nature. It was an ingeniously adaptable cipher, which Bacon could use to make anything signify anything. A secret message could be hidden in a group of objects or numbers, or even musical notation. Samuel Morse's dot-dash telegraph code, which revolutionized communication in the 1800s, and the on-off encoding in a modern computer both have parallels with Bacon's cipher. See also, positional numbers, the Rhine papyrus, decimals, logarithms, the mechanical computer, Boolean algebra, the Turing machine, cryptography. Introduction. By the late 1600s, Europe had become established as the cultural and scientific center of the world. The scientific revolution was well underway, inspiring a new, rational approach not only to the sciences, but to all aspects of culture and society. The Age of Enlightenment, as this period came to be known, was a time of significant socio-political change, and produced an enormous increase in the spread of knowledge and education during the 1700s. It was also a period of considerable progress in mathematics. Swiss giants. Building on the work of Newton and Leibniz, whose ideas were finding practical application in physics and engineering, the brothers Jacob and Johann Bernoulli further developed the theory of calculus in their Calculus of Variations, and several other mathematical concepts discovered in the 1600s. The elder brother, Jacob, is recognized for his work on number theory, but he also helped develop probability theory, introducing the law of large numbers. Along with their mathematically gifted children, the Bernoullis were the leading mathematicians of the early 1700s, making their hometown of Basel in Switzerland a center of mathematical study. It was here that Leonhard Euler, the next, and arguably greatest, Enlightenment mathematician, was born and educated. Euler was a contemporary and friend of Daniel and Nicholas Bernoulli, Johann's sons, and at an early age proved himself a worthy successor to Jacob and Johann. Aged only 20, he suggested a notation for the irrational number e, for which Jacob Bernoulli had calculated an approximate value. Euler published numerous books and treatises, and worked in every field of mathematics, often recognizing the links between apparently separate concepts of algebra, geometry, and number theory, which were to become the basis for further fields of mathematical study. For example, his approach to the seemingly simple problem of planning a route through the city of Königsberg, crossing each of its 7 bridges only once, uncovered much deeper concepts of topology, inspiring new areas of research. Euler's contributions to all fields of mathematics, but in particular calculus, graph theory, and number theory, were enormous, and he was also influential in standardizing mathematical notation. He is especially remembered for the elegant equation known as Euler's identity, which highlights the connection between fundamental mathematical constants such as E and pi. Other mathematicians. The Bernoullis and Euler tended to eclipse the achievements of the many other mathematicians of the 1700s. Among them was Christian Goldbach, a German contemporary of Euler's. In the course of his career, Goldbach had befriended other influential mathematicians, including Leibniz and the Bernoullis, and corresponded regularly with them about their theories. In a letter to Euler, he proposed the conjecture for which he is best known, that every even integer greater than 2 can be expressed as the sum of 2 primes, which remains unproven to this day. Others contributed to the development of the growing field of probability theory. Georges-Louis Leclerc, Comte de Buffon, for example, applied the principles of calculus to probability, and demonstrated the link between pi and probability, while another Frenchman, Abraham de Moivre, described the concept of normal distribution. An Englishman, Thomas Bayes, proposed the theorem of the probability of events based on knowledge of the past. In the latter part of the 18th century, France became the European center of mathematical inquiry, with Joseph-Louis Lagrange in particular emerging as a significant figure. Lagrange had made his name working with Euler, but later made important contributions to polynomials and number theory. New frontiers. As the century drew to a close, Europe was reeling from political revolutions that had toppled the monarchy in France and given birth to the United States of America. A young German, Carl Friedrich Gauss, published his fundamental theorem of algebra, marking the beginning of a spectacular career and a new period in the history of mathematics. In context. Key figure. Isaac Newton Field. Applied mathematics before. C. 330 BC. Aristotle believes it takes force to maintain motion. C. 1630 Galileo Galilei conducts experiments on motion and finds that friction is a retarding force. 1674 Robert Hooke writes an attempt to prove the motion of the Earth, and hypothesizes what will become Newton's first law. After 1905 Albert Einstein presents his theory of relativity, which challenges Newton's view of the force of gravity. 1977 Voyager 1 is launched. With no friction or drag in space, the craft keeps going due to Newton's first law, and exits the solar system in 2012. In using mathematics to explain the movement of the planets and of objects on Earth, Isaac Newton fundamentally changed the way we see the universe. He published his findings in 1687 in the 3-volume Philosophiae Naturalis Principia Mathematica, often called the Principia for short. Newton's second and third law help explain how scales work. When we weigh ourselves, our weight is a force, now measured in newtons. Newtons can be converted into measurements of mass, such as pounds. How the planets move. By 1667, Newton had already developed early versions of his 3 laws of motion and knew about the force needed to enable a body to move in a circular path. He used his knowledge of forces and German astronomer Johannes Kepler's laws of planetary motion to deduce how elliptical orbits were related to the laws of gravitational attraction. In 1686, English astronomer Edmund Halley persuaded Newton to write up his new physics and its applications to planetary motion. In his Principia, Newton used mathematics to show that the consequences of gravity were consistent with what had been observed experimentally. He analyzed the motion of bodies under the action of forces and posited gravitational attraction to explain the movement of the tides, projectiles, and pendulums, and the orbits of planets and comets. Laws of motion. Newton began Principia by stating his 3 laws of motion. The first says that a force is needed to create motion, and that this force may be from the gravitational attraction between 2 bodies or an applied force. The second law explains what is happening when objects are in motion. Newton said that the rate of change of momentum of a body is equal to the force acting on it. If a graph is plotted showing velocity against time, then the gradient at any point is the rate of acceleration. Newton's third law says that if 2 objects are in contact, the reaction forces between them cancel out, each pushing on the other with an equal force, but in opposing directions. An object resting on a table pushes down on it, and the table pushes back with an equal force. If this were not true, the object would move. Until Einstein's theory of relativity, the whole of mechanical physics was based on Newton's 3 laws of motion. Isaac Newton. Isaac Newton was born on Christmas Day in 1642 in Lincolnshire, England, and was brought up in early childhood by his grandmother. Newton studied at Trinity College, Cambridge, where he showed a fascination for science and philosophy. During the Great Plague in 1665-1666, the university was forced to close, and it was during this period that he formulated his ideas on flux science. Newton made significant discoveries in the fields of gravitation, motion, and optics, where he developed a rivalry with eminent English scientist Robert Hooke. One of several government positions he held was Master of the Royal Mint, where he oversaw the switch of the British currency from the silver to the gold standard. He was also President of the Royal Society. Newton died in 1727. Key work. 1687 Philosophiae Naturalis Principia Mathematica. See also, Syllogistic Logic, the problem of maxima calculus emi noter and abstract algebra. In context. Key figure. Jacob Bernoulli field probability before. Circa 1564 Gerolamo Cardano writes Liber de Ludo Ailey, the first work on probability. 1654 Pierre de Fermat and Blaise Pascal develop probability theory. After 1733 Abraham de Moivre proposes what becomes the central limit theorem. As the sample size increases, the results will more closely match normal distribution, or the bell curve. 1763 Thomas Bayes develops a way of predicting the chance of an outcome by taking into account the starting conditions related to that outcome. The law of large numbers is one of the foundations of probability theory and statistics. It guarantees that, over the long term, the outcomes of future events can be predicted with reasonable accuracy. This, for example, gives financial companies the confidence to set prices for insurance and pension products, knowing their chances of having to pay out, and ensures that casinos will always make a profit from their gambling customers, eventually. According to the law, as you make more observations of an event occurring, the measured probability of that outcome gets ever closer to the theoretical chance as calculated before any observations began. In other words, the average result from a large number of trials will be a close match to the expected value as calculated using probability theory, and increasing the number of trials will result in that average becoming an even closer match. The law was named by French mathematician Simeon Poisson in 1835, but its origin is credited to Swiss mathematician Jacob Bernoulli. His breakthrough, which he called the Golden Theorem, was published by his nephew in 1713 in the book Ars Conjectandi. Although not the first person to recognize the relationship between collecting data and predicting results, Bernoulli developed the first proof of this relationship by considering a game with two possible outcomes, a win or a loss. The theoretical chance of winning the game is W, and Bernoulli suspected that the fraction of games that resulted in a win would converge on W as the number of games increased. He proved this by showing that the probability of F being greater or less than W by a specified amount approached zero. As the game was repeated, we define the art of conjecture as the art of evaluating the probabilities of things, so that in our judgments and actions we can always base ourselves on what has been found to be the best. Jacob Bernoulli. The false probability. A coin toss is an example of the law of large numbers. Assuming that the chance of a heads or tails result is equal, the law dictates that after many tosses, half will have landed on heads, and half on tails. However, in the early stages, heads and tails are likely to be more unbalanced. For example, the first 10 tosses could be 7 heads and 3 tails. It might then seem most likely that the next toss will produce a tail. That, however, is the gambler's fallacy, where a person assumes that the outcomes of each game are connected. A gambler might assume that toss number 11 is likely to be a tail because the number of heads and tails must balance out, but the probability of heads or tails is the same in every toss, and the outcome of one toss occurs independently of any other. This is the starting point of all probability theory. After 1,000 tosses, the imbalance apparent in those first 10 tosses becomes negligible. When a referee flips a coin, there is no advantage, according to the law of large numbers, in a team captain basing a heads or tails choice on what has been called in previous games. Jacob Bernoulli. Born in Basel, Switzerland, in 1655, Jacob Bernoulli studied theology, but developed an interest in mathematics. In 1687, he became a professor of mathematics at the University of Basel, a position he held for the rest of his life. In addition to his work on probability, Bernoulli is remembered for discovering the mathematical constant E by calculating the growth of funds that received compound interest continuously in infinitesimal increments. He was also involved in the development of calculus, taking the side of Gottfried Leibniz against Isaac Newton in their rival claims to have invented a new mathematical field. Bernoulli worked on calculus with his younger brother Johann. However, Johann became jealous of his brother's achievements, and their relationship broke down several years before Jacob died in 1705. Key works: 1713 Ars Conjectandi, 1744 Opera. See also, Probability Normal Distribution, Bayes' Theorem, the Poisson Distribution, the Birth of Modern Statistics. In context. Key figure: Leonhard Euler field number theory before 1618 logarithms calculated from the number now known as E are listed in an appendix to a book on logarithms by John Napier. 1683 Jacob Bernoulli uses E in his work on compound interest. 1733 Abraham de Moivre discovers normal distribution, the way that values for most data cluster at a central point and taper off at the extremes. Its equation involves E. After 1815 Joseph Fourier's proof that E is irrational is published. 1873 French mathematician Charles Hermite proves that E is transcendental. The mathematical constant that became known as E, or Euler's number, 2.718, to an infinite number of decimal places, first appeared in the early 1600s, when logarithms were invented to help simplify complex calculations. Scottish mathematician John Napier compiled tables of logarithms to base 2.718, which worked particularly well for calculations involving exponential growth. These were later dubbed natural logarithms, because they can be used to mathematically describe many processes in nature, but with algebraic notation still in its infancy. Napier saw logarithms only as an aid to calculation involving the ratio of distances covered by moving points. In the late 1600s, Swiss mathematician Jacob Bernoulli used 2.718 to calculate compound interest, but it was Leonhard Euler, a student of Bernoulli's brother Johann, who first called the number E, Euler calculated e to 18 decimal places, writing his first work on e, the Meditatio, in 1727. However, it was not published until 1862. Euler explored e further in his 1748 Introductio. Leonhard Euler. Born in 1707 in Basel, Switzerland, Euler grew up in nearby Riehen. Taught initially by his father, a Protestant minister who had some mathematical training and was also a friend of the Bernoulli family, Euler developed a passion for mathematics. Although he entered university to study for the ministry, he switched to mathematics with the support of Johann Bernoulli. Euler went on to work in Switzerland and Russia, and became the most prolific mathematician of all time, contributing greatly to calculus, geometry, and trigonometry, among other fields. This was despite steadily losing his sight from 1738 and becoming blind in 1771. Working to the very end, he died in 1783 in St. Petersburg. Key works: 1748 Introductio in Analysum Infinitorium, 1862 Meditatio in Experimenta Explosion Tormentorum Nuper Instituta. Compound interest. One of the earliest appearances of E was in calculating compound interest, where the interest on a savings account, for example, is paid into the account to increase the amount saved, rather than being paid out to the investor. If the interest is calculated on a yearly basis, an investment of $100 at an interest rate of 3% per year would produce $100 1.03 equals $103 after 1 year. After 2 years, it would be 101.03 1.03 equals $106.09, and after 10 years it would be $100 1.0310 equals $134.39. The formula for this is A equals P, where A is the final amount, P is the original investment, R is the interest rate, and T is the number of years. If interest is calculated more often than annually, the calculation changes. For example, if interest is calculated monthly, the monthly rate is 12 of the yearly rate. 3 divided by 12 is equal to 0.25, so the investment after a year would be $100 1.002512 equals $103.04. If interest is calculated daily, the rate is 3 divided by 365 is equal to 0.008. And the amount after 1 year is $100 1.00008. 365 equals $103.05. The formula for this is A equals PNT, where N is the number of times the interest is calculated in each year. As the time intervals at which interest is calculated get smaller, the amount of interest yielded at the end of a year approaches A equals P. Bernoulli came close to working this out in his calculations, when he identified E as the limit of as n approaches infinity. The formula gives closer values for E as n increases. For example, n equals 1 gives a value for E of 2, n equals 10 gives a value for E of 2.5937. And n equals 100 gives a value for E of 2.7048. When Euler calculated a value for E correct to 18 decimal places, he probably used the sequence E equals 1 plus 1 plus 24 plus 120 plus 720, going up to 20 terms. He arrived at these denominators by using the factorial for each integer. The factorial of an integer is the product of the integer and all the integers below it, 2, 3, 4, 5 and so on, adding one more term in the product each time. This can be shown as E equals 1 plus 1 plus 2, plus 3, plus 4, in factorial notation. Euler calculated E to 18 decimal places, but noted that the decimals continued indefinitely. This means that E is irrational. In 1873, French mathematician Charles Hermite proved that E is also non-algebraic. It is not a number with a terminating decimal that can be used in a regular polynomial equation. This makes it a transcendental number, a real number that cannot be computed by solving an equation. Compounding interest yields a bigger total sum. The examples below show how a $10 principal investment accrues interest if the yearly interest rate is 100% versus compound interest paid at shorter intervals. The exponential function can be used to calculate compound interest. The function produces the curve y equals e, which cuts the y-axis at, and gets exponentially steeper. This graph also shows the tangent to the curve. The growth curve. Compound interest is an example of exponential growth. Such growth can be plotted on a graph and will appear as a curve. In the 1600s, English cleric Thomas Malthus posited that population also increases exponentially if there are no checks on its growth, such as war, famine, or food shortages. This means that the population continues to grow at the same rate, leading to ever larger totals. Constant population growth can be calculated with the formula P equals PRT, where P is the original population number, R is the growth rate, and T is time. Plotted on a graph, E shows other special properties. The graph of y equals E is a curve whose tangent at the coordinates also has a gradient of precisely 1. This is because the derivative of E is, in fact, E, and the derivative is used to find the tangent. The tangent is used to calculate the rate of change at a specific point on a curve. Because the derivative is E, the slope of the tangent line will always be the same as the y value. For the sake of brevity, we will always represent this number, 2.718281828, by the letter E. Leonard-Euler. Derangements. The various ways in which a set of items can be ordered are called permutations. For example, the set 1, 2, 3 can be arranged as 1, 3, 2 or 2, 1, 3 or 2, 3, 1 or 3, 1, 2 or 3, 2, 1. There are 6 total ways, including the original, as the number of permutations in a set is equal to the factorial of the highest integer, in this case 3. Euler's number is also significant in a type of permutation called a derangement. In a derangement, none of the items can remain in their original position. For 4 items, the number of possible permutations is 24, but to find the derangements of 1, 2, 3, 4, all other arrangements beginning with 1 must first be eliminated. There are 3 derangements starting with 2, 2, 1, 4, 3, 2, 3, 4, 1, and 2, 4, 1, 3. There are also 3 derangements starting with 3 and 3 starting with 4, making 9 in total. With 5 items, the total number of permutations is 120, and with 6 it is 720, making the task of finding all derangements a substantial one. Euler's number makes it possible to calculate the number of derangements in any set. This number equals the number of permutations divided by E, rounded to the nearest whole number. For example, for the set of 1, 2, 3, where there are 6 permutations, 6 divided by E equals 2.207, or 2 to the nearest whole number. Euler analyzed derangements of 10 numbers for Frederick the Great of Prussia, who hoped to create a lottery to pay off his debts. For 10 numbers, Euler found that the probability of getting a derangement is to an accuracy of 6 decimal places. Always at war, in summer with the Austrians, in winter with mathematicians. Jean-Laurent D'Alembert, French mathematician. Other uses. Euler's number is relevant in many other calculations, for example, in splitting up a number to discover which numbers in the partition have the largest product. With the number 10, partitions include 3 and 7, with a product of 21, or 6 and 4 to produce 24, or 5 and 5 to give 25, which is the maximum product for a partition of 10 using 2 numbers. With 3 numbers, 3, 3, 4 has a product of 36, but moving into fractional numbers, 333 is equal to 100,000 and 27 equals 37.037. The largest for 3 numbers. For a 4-way partition, 2222 is equal to 39. 0625, but in a 5-way split, 22222 is equal to 32. In short, 2 is equal to 25, 3 is equal to 37.037, 4 is equal to 39.0625, and 5 is equal to 32. This smaller result for a 5-way partition suggests that the optimal number of splits for 10 is between 3 and 4. Euler's number can help to find both the maximum product, as E equals 39.598, and number of partitions, 10 is equal to 3.678. To carbon date organic material, researchers test a sample, here from an ancient human bone, and use Euler's number to calculate its age from the rate of radioactive decay. The catenary, sometimes defined as the shape a hanging chain takes if it is only supported at its ends. A catenary is a curve with the formula y equals E plus E. Catenaries are often found in nature and in technology. For example, a square sail under pressure from the wind takes the form of a catenary. Arches in the shape of an inverted catenary are often used in architecture and construction due to their strength. For a long time, the catenary's shape was believed to be the same as that of a parabola. Dutch mathematician Christian Huygens, who coined the name catenary from the Latin catena in 1690, showed that, unlike a parabola, a catenary curve could not be given by a polynomial equation. Three mathematicians, Huygens, Gottfried Leibniz, and Johann Bernoulli, calculated a formula for the catenary, coming to the same conclusion. Their results were published together in 1691. In 1744, Euler described a catenoid, shaped like a wasted cylinder and produced by rotating a catenary around an axis. The Gateway Arch in St. Louis, Missouri is a flattened catenary arch, designed by Finnish-American architect Eero Saarinen in 1947. See also, positional numbers, irrational numbers, calculating pi decimals, logarithms. Probability, the law of large numbers, Euler's identity. In context. Key figures: Abraham de Moivre, Carl Friedrich Gauss fields. Statistics, probability before. 1710 British physician John Arbuthnot publishes a statistical proof of divine providence in relation to the number of men and women in a population. After. 1920 Karl Pearson, a British statistician, expresses regret about describing the Gaussian curve as the normal curve, because it gives the impression that all other probability distributions were abnormal. 1922 in the U.S., the New York Stock Exchange introduces the use of normal distribution to model the risks of investments. In the 18th century, French mathematician Abraham de Moivre made an important step forward in statistics. Building on Jacob Bernoulli's discovery of binomial distribution, de Moivre showed that events cluster around the mean. This phenomenon is known as normal distribution. Binomial distribution was first shown by Bernoulli in Ars Conjectandi, published in 1743. When a coin is flipped, there are two possible outcomes, success and failure. This type of test, with two equally likely outcomes, is called a Bernoulli trial. Binomial probabilities arise when a fixed number, n, of such Bernoulli trials, each with the same success, probability p, are carried out and the total number of successes is counted. The resulting distribution is written as b. Binomial distribution b can take values from 0 to n, centered on a mean of np. The bell curve is a visual illustration of normal distribution. The highest point of the curve represents the mean, which the values cluster around. Values become less frequent the further they are from the mean, so are least frequent at points A and C. Finding the mean. In 1721, Scottish Baronet Alexander Cumming gave de Moivre a problem concerning the expected winnings in a game of chance. De Moivre concluded that it came down to finding the mean deviation of binomial distribution. He wrote up his results in Miscellanea Analytica. De Moivre had realized that binomial outcomes cluster around their mean. On a graph, they plot an uneven curve that gets closer to the shape of a bell the more data is collected. In 1733, de Moivre was satisfied that he had found a simple way of approximating binomial probabilities using normal distribution, thus creating a bell curve for binomial distribution on a graph. He wrote up his findings as a short paper, then included it in the 1738 edition of his Doctrine of Chances. Using normal distribution. From the mid-1700s, the bell curve cropped up as a model for all kinds of data. In 1809, Carl Friedrich Gauss pioneered normal distribution as a useful statistical tool in its own right. French mathematician Pierre-Simon Laplace used normal distribution to model curves for random errors, such as measurement errors, in one of the first applications of a normal curve. In the 1800s, many statisticians studied variation in experimental results. British statistician Francis Galton used a device called the quincunx to study random variation. The board consisted of a triangular array of pegs through which beads dropped from top to bottom, where they collected in a series of vertical tubes. Galton measured how many beads were in each tube and described the resulting distribution as normal. His work, along with that of Karl Pearson, popularized the use of the term normal to describe what was also known as a Gaussian curve. Today, normal distribution is widely used to model statistical data, with applications ranging from population studies to investment analysis. Abraham de Moivre. Born in 1667, Abraham de Moivre was raised as a Protestant in Catholic France, and lived there until 1685, when Louis XIV expelled the Huguenots. Briefly imprisoned for his religious beliefs, de Moivre emigrated to England upon his release. He became a private mathematics tutor in London. He had hoped for a university teaching position, but he still faced some discrimination as a Frenchman in England. Nevertheless, de Moivre impressed and befriended many eminent scientists of the time, including Isaac Newton, and was elected as a Fellow of the Royal Society in 1697. As well as his work on distribution, de Moivre was best known for his work on complex numbers. He died in London in 1754. Key works: 1711 De Mensura Sortis, 1721, 30 Miscellanea Analytica, 1738 The Doctrine of Chances, 1756 The Doctrine of Chances. See also Probability, the law of large numbers, the fundamental theorem of algebra, Laplace's demon, the Poisson distribution, the birth of modern statistics. In context. Key figure: Leonhard Euler fields. Number theory, topology before. 1727 Euler develops the constant E, which is used in describing exponential growth and decay. After 1858 August Mobius extends Euler's graph theory formula to surfaces that are joined to form a single surface. 1895 Henri Poincaré publishes his paper Analysis Situs, in which graph theory is generalized to create a new area of mathematics known as topology. Graph theory and topology began with Leonhard Euler's attempt to find a solution to a mathematical puzzle, whether it was possible to make a circuit of the 7 bridges in Königsberg without crossing any bridge twice. The river flowed around an island and then forked. Realizing that the problem related to the geometry of position, Euler developed a new type of geometry to show that it was impossible to devise such a route. Distances between points were not relevant. The only thing that counted was the connections between points. Euler modeled the Königsberg Bridges problem by making each of the 4 land areas a point, and making the bridges arcs that joined the various points. This gave him a graph that represented the relationships between the land and the bridges. First graph theorem. Euler began from the premise that each bridge could be crossed only once, and each time a land area was entered it also needed to be exited, which required 2 bridges in order to avoid crossing any bridge twice. Each land area therefore needed to connect to an even number of bridges, with the possible exception of the start and finish. However, in the graph representing Königsberg, A is the endpoint of 5 bridges and B, C, and D are each the endpoint of 3. A successful route needs land areas to have an even number of bridges to enter and exit by. Only the start and end points can have an odd number. If more than 2 nodes have an odd number of arcs, then a route using each bridge only once is impossible. By showing this, Euler provided the first theorem in graph theory. The word graph is most often used to describe a Cartesian system of coordinates with points plotted using x and y axes. More generally, A graph consists of a discrete set of nodes connected by arcs. The number of arcs meeting at a node is called its degree. For the Königsberg graph, A has degree 5 and B, C, and D each have degree 3. A path that travels each arc once, and only once, is called an Eulerian path. The Königsberg bridges problem can be expressed as the question: is there an Eulerian or a semi-Eulerian path for the graph of Königsberg? Euler's answer is that such a graph must have at most 2 nodes of odd degree, but the Königsberg graph has 4 odd degree nodes. Read Euler, read Euler. He is our master in everything. Pierre-Simon Laplace. Network theory. Arcs on a graph may be weighted by assigning numerical values to them, for example, to represent the different lengths of roads on a map. A weighted graph is also called a network. Networks are used to model relationships between objects in many disciplines, including computer science, particle physics, economics, cryptography, sociology, biology, and climatology, usually with a view to optimizing a particular property, such as the shortest distance between 2 points. One application of networks is to address the so-called traveling salesperson problem. This involves finding the shortest route for a salesperson to travel from their home to a series of cities and back again. The puzzle was allegedly first set as a challenge on the back of a cereal box. In spite of advances in computing, no method exists that guarantees to always find the best solution, because the time this takes grows exponentially as the given number of cities increases. The city of Königsberg had 7 bridges linking 2 parts of the city to its 2 islands. Euler's graph shows that it is impossible to construct a route that visits each island and crosses each bridge only once. See also, coordinates. Euler's number, the complex plane, the Mobius strip topology. The butterfly effect, the 4-color theorem. In context. Key figure. Christian Goldbach field number theory before. C. 200 C. Diophantus of Alexandria writes his Arithmetica, in which he lays out key issues about numbers. 1202 Fibonacci identifies what becomes known as the Fibonacci sequence of numbers. 1643 Pierre de Fermat pioneers number theory. After 1742 Leonhard Euler refines the Goldbach conjecture. 1937 Soviet mathematician Ivan Vinogradov proves the ternary-Goldbach problem, a version of the conjecture. In 1742, Russian mathematician Christian Goldbach wrote to Leonhard Euler, the leading mathematician of the time. Goldbach believed he had observed something remarkable, that every even integer can be split into 2 prime numbers, such as 6 or 8. Euler was convinced that Goldbach was right, but he could not prove it. Goldbach also proposed that every odd integer above 5 is the sum of 3 primes, and concluded that every integer from 2 upward can be created by adding together primes. These additional proposals are dubbed weak versions of the original strong conjecture, as they would follow naturally if the strong conjecture were true. Manual and electronic methods have, as yet, failed to find any even number that does not conform to the original strong conjecture. In 2013, a computer tested every even number up to 1018 without finding one. The bigger the number, the more pairs of primes can create it, so it seems highly likely that the conjecture is valid and no exception will be found. Mathematicians, however, require a definitive proof. Over centuries, different, weak, versions of the conjecture have been proved, but no one to date has proved the strong conjecture, which seems destined to defeat even the brightest minds. UCLA's Terence Tao, winner of the Fields Medal in 2006 and the Breakthrough Prize in Mathematics in 2015, published a rigorous proof of a weak Goldbach conjecture in 2012. See also, Mersenne primes, the law of large numbers, the Riemann hypothesis, the prime number theorem. In context. Key figure. Leonhard Euler field number theory before. 1714 Roger Coates, the English mathematician who proofread Newton's Principia, creates an early formula similar to Euler's, but using imaginary numbers and a complex logarithm. After 1749, Abraham de Moivre uses Euler's formula to prove his theorem, which links complex numbers and trigonometry. 1934, Soviet mathematician Alexander Gelfand shows that e pi is transcendental, that is, irrational and still irrational when raised to any power. Formulated by Leonhard Euler in 1747, the equation known as Euler's identity, e plus 1 is equal to 0, encompasses the 5 most important numbers in mathematics: 0, which is neutral for addition and subtraction; 1, which is neutral for multiplication and division, I, the fundamental imaginary number, and pi, 3.142. The ratio of a circle's circumference to its diameter, which occurs in many equations in mathematics and physics. 2 of these numbers, e and I, were introduced by Euler himself. His genius lay in combining all 5 milestone numbers with 3 simple operations, raising a number to a power, multiplication, and addition. Complex powers. Mathematicians such as Euler asked themselves if it would be meaningful to raise a number to a complex power, a complex number being a number that combines a real number with an imaginary one, such as a plus b, where a and b are any real numbers. When Euler raised the constant e to the power of the imaginary number I multiplied by pi, he discovered that it equals 1. Adding 1 to both sides of the equation produces Euler's identity, e plus 1 is equal to 0. The equation's simplicity has led mathematicians to describe it as elegant, a description reserved for proofs that are profound yet also unusually succinct. It is simple, yet incredibly profound. It comprises the 5 most important mathematical constants. David Percy, British mathematician. See also, calculating pi, trigonometry, imaginary and complex numbers, logarithms, Euler's number. In context. Key figure. Thomas Bayes' field probability before 1713. Jacob Bernoulli's Ars Conjectandi, published after his death, sets out his new mathematical theory of probability. 1718. Abraham de Moivre defines the statistical independence of events in his book The Doctrine of Chances. After 1774. In his memoir on the probability of the causes of events, Pierre-Simon Laplace introduces the principle of inverse probability. 1992. The International Society for Bayesian Analysis is founded to promote the application and development of Bayes' theorem. In 1763, Richard Price, a Welsh minister and mathematician, published a paper called An Essay Towards Solving a Problem in the Doctrine of Chances. Its author, the Reverend Thomas Bayes, had died 2 years earlier, leaving the paper to Price in his will. It was a breakthrough in the modeling of probability and is still used today in areas as diverse as locating lost aircraft and testing for disease. Jacob Bernoulli's book Ars Conjectandi showed that as the number of identically distributed, randomly generated variables increases, so their observed average gets closer to their theoretical average. For example, if you toss a coin for long enough, the number of times it comes up heads will get closer and closer to half the total of tosses, a probability of 0.5. In 1718, Abraham de Moivre grappled with the mathematics underpinning probability. He demonstrated that, provided the sample size was large enough, the distribution of a continuous random variable, people's heights, for example, averaged out into a bell-shaped curve, later named the normal distribution, by German mathematician Karl Gauss. If a disease affects 5% of the population and is diagnosed using a test with 90% accuracy, you might assume that the probability of having the disease if you test positive, p, is 90%. However, Bayes' theorem factors in the false results produced by the test's 10% inaccuracy, p. Working out probabilities. Most real-world events, however, are more complicated than the toss of a coin. For probability to be useful, mathematicians needed to determine how an event's outcome could be used to draw conclusions about the probabilities that led to it. This reasoning based on the causes of observed events, rather than using direct probabilities, such as the 50% chance of a heads coin toss, became known as inverse probability. Problems that deal with the probabilities of causes are called inverse probability problems and might involve, for example, observing a bent coin landing on heads 13 times out of 20 and then trying to determine whether the probability of that coin landing on heads lies somewhere between 0.4 and 0.6. To show how to calculate inverse probabilities, Bayes considered two interdependent events, event A and event B. Each has a probability of occurring, P and P, with P for each being a number between 0 and 1. If event A occurs, it alters the probability of event B happening, and vice versa. To denote this, Bayes introduced conditional probabilities. These are given as P, the probability of A given B, and P, the probability of B given A. Bayes managed to solve the problem of how all four probabilities related to one another with the equation P equals PPP. Thomas Bayes. The son of a nonconformist minister, Thomas Bayes was born in 1702 and grew up in London. He studied logic and theology at the University of Edinburgh and followed his father into the ministry, spending much of his life leading a Presbyterian chapel in Tunbridge Wells, Kent. Although little is known of Bayes' life as a mathematician, in 1736 he anonymously published an introduction to the doctrine of flux science, and a defense of the mathematicians against the objections of the author of the Analyst, in which he defended Isaac Newton's calculus foundations against the criticisms of the philosopher Bishop George Berkeley. Bayes was made a Fellow of the Royal Society in 1742 and died in 1761. Key work. 1736 An Introduction to the Doctrine of Flux Science, and a defense of the mathematicians against the objections of the author of the Analyst. See also, Probability, the law of large numbers, normal distribution, Laplace's demon, the Poisson distribution, the birth of modern statistics, the Turing machine, cryptography. In context. Key figure. Joseph Louis Lagrange field algebra before. 628 Brahmagupta publishes a formula for solving many quadratic equations. 1545 Gerolamo Cardano creates formulae for resolving cubic and quartic equations. 1749 Leonhard Euler proves that polynomial equations of degree n have exactly n complex roots. After 1799 Carl Gauss publishes the first proof of the fundamental theorem of algebra. 1824 in Norway, Niels Henrik Abel completes Paolo Ruffini's 1799 proof that there is no general formula for the quintic equation. Polynomial equations involving numbers and a single unknown quantity are a powerful tool for solving real-world problems. An example of a polynomial equation is x plus 41 is equal to 0. While such equations can be solved approximately by repeated numerical calculations, solving them exactly was not achieved until the 1700s. The quest led to many mathematical innovations, including new types of numbers, such as negative and complex numbers, as well as modern algebraic notation and group theory. Searching for solutions. The Babylonians and ancient Greeks used geometrical methods to solve problems that are now usually expressed by quadratic equations. In medieval times, more abstract algorithmic approaches were established, and by the 1500s, mathematicians knew certain relations between the coefficients of a polynomial equation and its roots, and had devised formulas to solve cubic and quartic equations. In the 1600s, a general theory of polynomial equations, now called the fundamental theorem of algebra, took shape. This stated that an equation of degree n has exactly n roots or solutions, which may be real or complex numbers. An algebraic equation is made up of variables and coefficients. The highest power of the equation determines how many solutions it has. In this case, there are 3 solutions. Roots and permutations. In his reflections on the algebraic resolution of equations, French-Italian mathematician Joseph Louis Lagrange introduced a general approach for solving polynomial equations. His work was theoretical. He investigated the structure of polynomial equations to find the circumstances under which a formula could be found for solving them. Lagrange combined the technique of using a related, lower-degree polynomial equation whose coefficients were related to the coefficients of the original equation. With a striking innovation, he considered the possible permutations of the roots. Lagrange's insight into the symmetries that arose from these permutations showed why the cubic and quartic equations could be solved by formulas, and showed why a formula for the quintic equation needed a different approach. Within 20 years of Lagrange's work, Italian mathematician Paolo Ruffini began to prove that there was no general formula for the quintic equation. Lagrange's investigation into permutations formed the basis of the even more abstract and general group theory advanced by French mathematician Évariste Galois, who used it to prove why it is impossible to resolve equations of degree 5 or higher algebraically, that is, why there is no general formula for solving such equations. Joseph Louis Lagrange. Born Giuseppe Lodovico Lagrangia in Turin in 1736, Lagrange embraced his family's French heritage and went by the French version of his name. As a young mathematician, self-taught, he worked on the Tautochron problem and developed a new formal method to find the function that solved such problems. At the age of 19, he wrote to Leonhard Euler, who recognized his talent. Lagrange applied his method, which Euler named the calculus of variations, to study a wide range of physical phenomena, including the vibration of strings. In 1766, at Euler's recommendation, he was made director of mathematics at the Berlin Academy, and in 1787 he moved to the Académie des Sciences in Paris. Despite being an academic and a foreigner, Lagrange survived the French Revolution and Reign of Terror, and died in Paris in 1813. Key works: 1771 Reflections on the Algebraic Resolution of Equations, 1788 Analytical Mechanics, 1797 Theory of Analytic Functions. See also: Quadratic Equations, Algebra, the Binomial Theorem, Cubic Equations, Huygens's Tautochron Curve, the Fundamental Theorem of Algebra Group Theory. In context. Key figure: Georges Louis Leclerc, Comte de Buffon Field Probability before 1666 Liber de Ludo Eli by Italian mathematician Gerolamo Cardano is published. 1718 Abraham de Moivre publishes The Doctrine of Chances, the first textbook on probability. After 1942-46 The Manhattan Project, a U.S.-led body for developing nuclear weapons, makes extensive use of Monte Carlo methods. Late 1900s quantum Monte Carlo methods are used to explore particle interactions in microscopic systems. In 1733, the mathematician and naturalist Georges Leclerc, the Comte de Buffon, raised, and answered, a fascinating question. If a needle is dropped onto a series of parallel lines, all the same width apart, what is the likelihood that the needle will cross one of the lines? Now known as Buffon's needle experiment, it was one of the earliest probability calculations. An elegant illustration. Buffon originally used the needle experiment to estimate pi, the ratio of a circle's circumference to its diameter. He did this by dropping a needle of length L many times onto a series of parallel lines distance d apart, where d is greater than the needle's length. Buffon then counted the number of times the needle crossed the line as a proportion of total attempts and came up with the formula that pi is approximately equal to twice the length of the needle L, divided by the distance multiplied by the proportion of needles crossing the line, pi 2L divided by dp. The probability of the needle crossing a line can be calculated by multiplying each side of the formula by p, then dividing each side by pi to get p2L divided by pi d. The relationship with pi can be used in a number of probability problems. One example involves a quarter circle, inscribed in a square, which curves from the top left corner of the square to the bottom right. The bottom horizontal edge of the square is the x-axis and the left vertical edge is the y-axis, with a value of 0 in the lower left corner and 1 in the corners at each end of the curve. When two numbers between 0 and 1 are chosen at random as the x and y coordinates, whether the point will lie inside the quarter circle or outside it can be deduced by examining where A is the x coordinate and b is the y coordinate. The result is 1 for points outside the curve and 1 for points within it. The point is chosen at random, so could be anywhere in the square. Points on the line of the quarter circle can be counted as a success. The chance of success is pi r divided by 4. If the radius is 1, r equals 1, so the area is just pi, for a quarter circle, divide pi by 4 to get approximately 0.78. The whole area is the area of the square, which is 1 is equal to 1, so the probability of landing in the shaded area is approximately 0.78 divided by 1 is equal to 0.78. Using pi, the probability of a randomly chosen point falling within the quarter circle in this square can be calculated as roughly 78%. The Monte Carlo method. This problem is an example of a wider class of experiments that employ a statistical approach called the Monte Carlo method, a code name coined by Polish-American scientist Stanislaw Ulam and his colleagues for the random sampling used during secret work on nuclear weapons in World War II. Monte Carlo methods went on to be useful in modern applications, especially once computers made it far less time-consuming to repeat a probability experiment over and over again. Buffon's needle experiment demonstrated how probability can be connected to pi. Buffon classed needles as successful if they crossed a line when dropped, or unsuccessful if they didn't, then calculated the probability of success. In wind energy yield analysis, the predicted energy output of a wind farm during its lifetime is calculated, giving different levels of uncertainty, by using Monte Carlo probability methods. Georges Louis Leclerc, Comte de Buffon. Born in Montbard, France, in 1707, Georges Louis Leclerc was urged by his parents to pursue a career in law, but was more interested in botany, medicine, and mathematics, which he studied at the University of Angers, France. At the age of 20, he explored the binomial theorem. Independently wealthy, Buffon was able to write and study tirelessly, corresponding with many of the scientific elite of his day. His interests were wide-ranging, and his output was immense, on topics ranging from shipbuilding to natural history and astronomy. The Comte also translated a number of scientific works. Appointed keeper of the Jardin du Roi, the Royal Botanical Gardens in Paris, in 1739, Buffon enriched its collections and doubled its size. He held the post until his death in Paris in 1788. Key works: 1749, 1786 Histoire naturelle, 1778 Les époques de la nature. The Epochs of Nature. See also, Calculating Pi Probability, the Law of Large Numbers, Bayes' Theorem, The Birth of Modern Statistics. In context. Key figure: Carl Gauss field algebra before 1629. Albert Girard states that a polynomial of degree n will have n roots. 1746. The first attempt at a proof of the fundamental theorem of algebra is made by Jean d'Alembert. After 1806, Robert Argand publishes the first rigorous proof of the FTA that allows polynomials with complex coefficients. 1920, Alexander Ostrowski proves the remaining assumptions in Gauss's proof of the FTA. 1940, Helmuth Nesser gives the first constructive variant of the Argand FTA proof that allows for the roots to be found. This method of solving problems by honest confession of one's ignorance is called algebra. Mary Everest Boole, British mathematician. An equation asserts that one quantity is equal to another, and provides a means of determining an unknown number. Since Babylonian times, scholars have sought solutions to equations, periodically encountering seemingly insoluble examples. In the 5th century BC, Hippasus' attempts to resolve x equals 2 and his realization that was irrational are said to have led to his death for betraying Pythagorean beliefs. Some 800 years later, Diophantus had no knowledge of negative numbers, so could not accept an equation where x is negative, such as 4 equals 4x plus 20, where x is minus 4. Polynomials and roots. In the 1700s, one of the most studied areas of mathematics involved polynomial equations. These are often used to solve problems in mechanics, physics, astronomy, and engineering, and involve powers of an unknown value, such as x. The root of a polynomial equation is a specific numerical value that will replace the unknown value to make the polynomial equal 0. In 1629, French mathematician Albert Girard showed that a polynomial of degree n will have n roots. The quadratic equation x plus 4x minus 12 is equal to 0, for example, has two roots, x equals 2 and x equals minus 6, both of which produce the answer 0. It has two roots because of the x term 2 is the equation's highest power. If any quadratic equation is drawn on a graph, these roots can be easily found. They are where the line touches the x-axis. Although his theorem was useful, Girard's work was hindered by the fact that he had no concept of complex numbers. These would be key to producing a fundamental theorem of algebra for solving all possible polynomials. Girolamo Cardano encountered negative roots while working on cubic equations in the 1500s. His acceptance of these as valid solutions was an important step in algebra. Complex numbers. The collection of all positive and negative, rational and irrational numbers together make up the real numbers. Some polynomials, however, do not have real number roots. This was a problem faced by Italian mathematician Girolamo Cardano and his peers in the 1500s. While working on cubic equations, they found that some of their solutions involved square roots of negative numbers. This seemed impossible, because a negative number multiplied by itself produces a positive result. The problem was solved in 1572 when another Italian, Raffaele Bombelli, set out the rules for an extended number system that included numbers such as alongside the real numbers. In 1751, Leonhard Euler investigated the imaginary roots of polynomials, and called the imaginary unit, or I. All imaginary numbers are multiples of I, combining the real and the imaginary, such as a plus b, where a and b are any real numbers, and I equals creates what is called a complex number. Once mathematicians had accepted the necessity of negative and complex numbers for solving certain equations, the question remained as to whether finding roots of higher degree polynomials would require the introduction of yet new types of number. Euler and other mathematicians, notably Karl Gauss in Germany, would seek to address this question, eventually concluding that the roots of any polynomial are either real or complex numbers. No further types of number are needed. Imaginary numbers are a fine and wonderful refuge of the divine spirit. Gottfried Leibniz. Karl Gauss. Born in Brunswick, Germany, in 1777, Karl Gauss showed his mathematical talents early. Aged only 3, he corrected an error in his father's payroll calculations, and by the age of 5 he was taking care of his father's accounts. In 1795, he entered Göttingen University, and in 1798, he constructed a regular heptadecagon using only a ruler and compasses, the biggest advance in polygon construction since Euclid's geometry some 2,000 years earlier. Gauss's arithmetical investigations, written at the age of 21 and published in 1801, was key to defining number theory. Gauss also made advances in astronomy, cartography, the study of electromagnetism, and the design of optical instruments. However, he kept many of his ideas to himself. A great number were discovered in his unpublished papers after his death in 1855. Key work. 1801 Disquisitions Arithmetici. Early research. The FTA can be stated in a number of ways, but its most common formulation is that every polynomial with complex coefficients will have at least one complex root. It can also be stated that all polynomials of degree n containing complex coefficients have n complex roots. The first significant attempt at proving the FTA was made in 1746 by French mathematician Jean-Laurent D'Alembert in his Recherches sur le calcul intégral. D'Alembert's proof argued that if a polynomial p with real coefficients has a complex root, x equals a plus ib, then it also has a complex root, x equals aib. To prove this theorem, he used a complicated idea now known as D'Alembert's lemma. In mathematics, a lemma is an intermediary proposition used to solve a bigger theorem. However, D'Alembert did not prove his lemma satisfactorily. His proof was correct, but contained too many holes to satisfy his fellow mathematicians. Later attempts to prove the FTA included those of Leonhard Euler and Joseph Louis Lagrange. While useful to later mathematicians, these were also unsatisfactory. In 1795, Pierre-Simon Laplace tried an FTA proof using the polynomials. Discriminate, a parameter determined from its coefficients which indicates the nature of its roots, such as real or imaginary. His proof contained an unproved assumption that D'Alembert had avoided, that a polynomial will always have roots. There are only two kinds of certain knowledge: awareness of our own existence and the truths of mathematics. Jean D'Alembert. Jean D'Alembert was the first to attempt to prove the FTA. In France, it is called the D'Alembert-Gauss theorem, acknowledging the influence of D'Alembert on Gauss. Gauss's proof. In 1799, at the age of 21, Carl Friedrich Gauss published his doctoral thesis. It began with a summary and criticism of D'Alembert's proof, among others. Gauss pointed out that each of these earlier proofs had assumed part of what they were trying to prove. One such assumption was that polynomials of odd degree always have a real root. This is true, but Gauss argued that the point needed to be proved. His first proof was based on assumptions about algebraic curves. Although these were plausible, they were not rigorously proved in Gauss's work. It was not until 1920, when Ukrainian mathematician Alexander Ostrowski published his proof, that Gauss's assumptions could all be justified. Arguably, Gauss's first, geometric proof suffered for being premature. In 1799, the concepts of continuity and of the complex plane, which would have helped him explain his ideas, had not yet been developed. Argand's additions. Gauss published an improved proof of the FTA in 1816 and a further refinement at his Golden Jubilee lecture in 1849. Unlike his first geometric approach, his second and third proofs were more algebraic and technical in nature. Gauss published 4 proofs of the FTA, but did not fully resolve the problem. He failed to address the obvious next step. Although he had established that every real number equation would have a complex number solution, he had not considered equations built from complex numbers such as x equals I. In 1806, Swiss mathematician Jean-Robert Argand found a particularly elegant solution. Any complex number z can be written in the form a plus by, whereas the real part of z and by is the imaginary part. Argand's work allowed complex numbers to be represented geometrically. If the real numbers are drawn along the x-axis and the imaginary numbers are drawn along the y-axis, then the whole plane between them becomes the realm of the complex numbers. Argand proved that the solution for every equation built from complex numbers could be found among the complex numbers on his diagram, and that there was therefore no need to extend the number system. Argand's was the first truly rigorous proof of the FTA. I have had my results for a long time, but I do not yet know how to arrive at them. Carl Gauss. Legacy of the theorem. The proofs by Gauss and Argand established the validity of complex numbers as roots of polynomials. The FTA stated that anyone faced with solving an equation built from real numbers could be sure that they would find their solution within the realm of complex numbers. These groundbreaking ideas formed the foundations of complex analysis. Mathematicians since Argand have continued to work on proving the FTA using new methods. In 1891, for example, German Karl Weierstrass created a method, now known as the Durand-Kerner method, due to its rediscovery by mathematicians in the 1960s, for simultaneously finding all of the roots of a polynomial. Applications of the FTA. An Einstein ring, first discovered in 1998, is the deformation of light from a source into a ring through gravitational lensing. Research on the fundamental theorem of algebra has led to breakthroughs in other fields. In the 1990s, British mathematicians Terence Shaw Small and Alan Wilmshurst extended the FT8 to harmonic polynomials. These may have an infinite number of roots, but in some cases, there are a finite number. In 2006, American mathematicians Dmitry Kovinson and Ginevra Newman proved that there was an upper limit to the number of roots of a certain class of harmonic polynomials. After publishing their results, they were told that their proof settled a conjecture by South Korean astrophysicist Sun Hong Rai. Her conjecture concerned images of distant astronomical light sources. Massive objects in the universe bend passing light rays from distant sources in a phenomenon called gravitational lensing, creating multiple images seen through a telescope. Rai posited that there would be a maximum number of images produced. This turned out to be exactly the upper bound found by Kovinson and Newman. See also, quadratic equations, negative numbers, algebra, cubic equations, imaginary and complex numbers, the algebraic resolution of equations, the complex plane. Introduction. Progress in mathematics accelerated through the 1800s, with science and mathematics now becoming respected academic studies. As the Industrial Revolution spread and 1848's Year of Revolution saw nationalism surge across old empires, there was a renewed drive to understand the workings of the universe in scientific terms, rather than through religion or philosophy. Pierre-Simon Laplace, for example, applied the theories of calculus to celestial mechanics. He proposed a form of scientific determinism, saying that with the relevant knowledge of moving particles, the behavior of everything in the universe could be predicted. Another characteristic of 19th-century mathematics was its increasing tendency toward the theoretical. This trend was fostered by the influential work of Carl Friedrich Gauss, regarded by many in the field as the greatest of all mathematicians. He dominated the study of mathematics for much of the first half of the century, making contributions to the fields of algebra, geometry, and number theory, and giving his name to such concepts as Gaussian distribution, Gaussian function, Gaussian curvature, and Gaussian error curve. New fields. Gauss was also a pioneer of non-Euclidean geometries, which epitomized the revolutionary spirit of 19th-century mathematics. The subject was taken up by Nikolai Lobachevsky and János Bolyai, who independently developed theories of hyperbolic geometry and curved spaces, resolving the problem of Euclid's parallel postulate. This opened up a completely new approach to geometry, paving the way for the nascent field of topology, which was also influenced by the possibility of more than 3 dimensions offered by William Hamilton's discovery of quaternions. Perhaps the best known of the pioneers of topology is August Mobius, inventor of the Mobius strip, which had the unusual property of being a 2-dimensional surface with only one side. Non-Euclidean geometries were further developed by Bernhard Riemann, who identified and defined different types of geometry in multiple dimensions. Riemann did not confine his studies to geometry, however. As well as his work on calculus, he made important contributions to number theory, following in the footsteps of Gauss. The Riemann hypothesis, derived from the Riemann zeta function concerning complex numbers, is as yet unsolved. Other notable discoveries in number theory at this time include the creation of set theory and the description of an infinity of infinities of George Cantor, Eugene Catalan's conjecture about the powers of natural numbers, and the application of elliptic functions to number theory proposed by Carl Gustav Jacob Jacobi. Jacobi was, like Riemann, multi-talented, often linking different fields of mathematics in new ways. His primary interest was in algebra, another area of mathematics that was becoming increasingly abstract during the 1800s. The groundwork for the growing field of abstract algebra was laid by Évariste Galois, who, although he died young, also developed group theory while determining a general algebraic method for solving polynomial equations. New technologies. Not all mathematics in this period was purely theoretical, and even some of the abstract concepts soon found more practical applications. Simeon Poisson, for example, used his knowledge of pure mathematics to develop ideas such as the Poisson distribution, a key concept in the field of probability theory. Charles Babbage, on the other hand, responded to practical demand for a means of accurate and quick calculation with his mechanical calculating device, the difference engine. In so doing, he laid the groundwork for the invention of computers. Babbage's work in turn inspired Ada Lovelace to devise the forerunner of modern computer algorithms. Meanwhile, there were other developments in mathematics that were to have far-reaching implications for later technological progress. Using algebra as his starting point, George Boole devised a form of logic based on a binary system, and using the operators AND, OR, and NOT. These became the foundation of modern mathematical logic, but just as importantly paved the way for the language of computers almost a century later. In context. Key figure. Jean-Robert Argand field number theory before. 1545 Italian scholar Girolamo uses negative square roots to solve cubic equations in his book Ars Magna. 1637 French philosopher and mathematician René Descartes develops a way to plot algebraic expressions as coordinates on a grid. After 1843 Irish mathematician William Hamilton extends the complex plane by adding two more imaginary units to create quaternions, expressions that are plotted in a 4D space. 1859 By merging two complex planes, Bernhard Riemann develops a 4D surface to help him analyze complex functions. After centuries of suspicion, mathematicians finally embraced the concept of negative numbers in the 1700s. They did so by using imaginary numbers in algebra. In 1806, the key contribution of Swiss-born mathematician Jean-Robert Argand was to plot complex numbers as coordinates on a plane created by two axes, x for real numbers and y for imaginary numbers. This complex plane provided the first geometrical interpretation of the distinctive properties of complex numbers. There can be very little science and technology that is not dependent on complex numbers. Keith Devlin, British mathematician. Algebraic roots. Imaginary numbers had emerged in the 1500s when Italian mathematicians such as Girolamo Cardano and Niccolò Fontana Tartaglia found that solving cubic equations required a square root of a negative number. The square of a real number cannot be negative. Any real number multiplied by itself results in a positive, so they decided to treat as a new unit that operated separately from the real numbers. Leonard Euler first used I to denote the imaginary unit in his attempts to prove the fundamental theorem of algebra. This theorem states that all polynomial equations of degree n have n roots. This means that if x is the highest power in an algebraic expression made up of a single variable and real coefficients, the expression has a degree of 2, and also 2 roots. Roots are values of x that make the polynomial equal to 0. Many seemingly simple polynomials, however, such as x plus 1, do not equal 0 if x is a real number. Plotting x plus 1 on a graph with an x and y axis creates a neat curve that never passes through the origin, or point. To make the FTA work for x plus 1, Gauss and others used real numbers combined with imaginary numbers to create complex numbers. All numbers are in essence complex. For example, the real number 1 is the complex number 1 plus 0i, while the number I is 0 plus I. The equation x plus 1 can equal 0 when x is I or I. An Argand diagram uses the x and y axes to represent real numbers and imaginary numbers, combining them to plot complex numbers. This diagram shows two numbers, 3 plus 5i and 7 plus 2i. Argand's discovery. As Argand began to plot complex numbers, he discovered that the imaginary number I does not get bigger if raised to higher powers. Instead, it follows a four-step pattern that repeats infinitely: I equals I equals 1, I equals I equals 1, I equals I, and so on. This can be visualized on the complex plane. Multiplying real numbers by imaginary numbers produces 90 degrees rotations through the complex plane. So 1i equals I, which does not appear on the real number x-axis at all, but on the imaginary y-axis. Continuing to multiply by I results in more 90 degrees rotations, which is why every 4 multiplications arrive back at the start point. Plots of complex numbers, or Argand diagrams, make complicated polynomials easier to solve. The complex plane is now a powerful tool that works far beyond the interests of number theory. Jean-Robert Argand. Little is known of Jean-Robert Argand's early life. He was born in Geneva in 1768, but appears to have had no formal education in mathematics. In 1806, he moved to Paris to manage a bookshop, and self-published the work containing the geometrical interpretation of complex numbers for which he is known. Argand's essay was republished in a mathematics journal in 1813, and in the next year, he used the complex plane to produce the first rigorous proof of the fundamental theorem of algebra. Argand published 8 more articles before his death in Paris in 1822. Key work: 1806 Essai sur une manière de représenter les quantités imaginaires dans les constructions géométriques. See also, quadratic equations, cubic equations, imaginary and complex numbers, coordinates, the fundamental theorem of algebra. In context. Key figure: Joseph Fourier field. Applied mathematics before 1701 in France, Joseph Sauveur suggests that vibrating strings oscillate with many waves of different lengths at the same time. 1753 Swiss mathematician Daniel Bernoulli shows that a vibrating string consists of an infinite number of harmonic oscillations. After 1965 in the US, James Cooley and John Tukey developed the fast Fourier transform, an algorithm that is able to speed up Fourier analysis. 2000's Fourier analysis is used to create a number of speech recognition programs for computers and smartphones. The sound created by vibrating strings has been a topic of research for more than 2,500 years. In about 550 BC, Pythagoras discovered that if you take 2 taut strings of the same material and the same tension, but one is twice the length of the other, the short string will vibrate with twice the frequency of the longer string and the resulting notes will be an octave apart. 2 centuries later, Aristotle suggested that sound traveled through the air in waves, although he incorrectly thought that higher-pitched sounds traveled faster than lower-pitched ones. In the 1600s, Galileo recognized that sounds are produced by vibrations. The higher the frequency of the vibrations, the higher the pitch of the sound we perceive. Sounds are made of a complex series of tones. Fourier analysis can separate out pure tones, which can be represented as sine waves on a graph, from each other. Tones have frequency, which determines pitch, and amplitude, which determines volume. Heat and harmony. By the end of the 1600s, physicists including Joseph Sauveur were making great strides in studying the relationships between the waves in stretched strings and the pitch and frequency of sounds that they produced. In the course of their research, mathematicians showed that any string will support a potentially infinite series of vibrations, starting from the fundamental and including its harmonics. The pure tone of a single pitch is produced by a smooth repetitive oscillation called a sine wave. The sound quality of a musical instrument results principally from the number and relative intensities of the harmonics present in the sound, or its harmonic content. The result is a variety of waves interfering with each other. Joseph Fourier was attempting to solve the problem of how heat diffused through a solid object. He developed an approach that would allow him to calculate the temperature at any location within an object, at any time after a source of heat had been applied to one of its edges. Fourier's studies of heat distribution showed that no matter how complex a waveform, it could be broken down into its constituent sine waves, a process that is now called Fourier analysis. Since heat in the form of radiation is a wave, Fourier's discoveries about heat distribution had applications to the study of sound. A sound wave can be understood in terms of the amplitudes of its constituent sine waves, a set of numbers that is sometimes referred to as the harmonic spectrum. Today, Fourier analysis plays a key role in many applications including digital file compression, analyzing MRI scans, speech recognition software, musical pitch correction software, and determining the composition of planetary atmospheres. Fourier analysis of the way materials vibrate allows engineers to construct buildings that resonate at different frequencies from a typical earthquake, and thus avoid the kind of damage that occurred in Mexico City in 2017. Joseph Fourier. Jean-Baptiste Joseph Fourier was born in Auxerre, France, in 1768. A tailor's son, he went to military school, where his keen interest in mathematics led him to become a successful teacher of the subject. Fourier's career was disrupted by two arrests, one for criticizing the French Revolution, the other for supporting it, but in 1798, he accompanied Napoleon's forces into Egypt as a diplomat. Napoleon later made him a baron, and then a count. After Napoleon's fall in 1815, Fourier moved to Paris to become director of the Statistical Bureau of the Seine, where he pursued his studies in mathematical physics, including work on the Fourier series. In 1822, Fourier was made the secretary of the French Academy of Sciences, a post he held until his death in 1830. Fourier is one of 72 scientists whose names are inscribed on the Eiffel Tower. Key work: 1822 Théorie analytique de l'échelle. See also Pythagoras trigonometry, Bessel functions, elliptic functions, topology, the Langlands program. In context. Key figure: Pierre-Simon Laplace field. Mathematical philosophy before 1665. Calculus is developed by Isaac Newton to analyze and describe the motion of falling bodies and other complex mechanical systems. After 1872, Ludwig Boltzmann uses statistical mechanics to show how the thermodynamics of a system always results in an increase in entropy. 1963, Edward Lorenz describes the Lorenz attractor, a model that produces chaotic results with every tiny change to the initial parameters. 1872, American mathematician David Walpert disproves Laplace's demon by treating the intellect as a computer. In 1814, Pierre-Simon Laplace, a French mathematician who combined mathematics and science with philosophy and politics, presented a thought experiment now known as Laplace's demon. Laplace never used the word demon himself. It was introduced in later retellings, evoking a supernatural being made godlike by mathematics. Laplace imagined an intellect that could analyze movements of all atoms in the universe in order to accurately predict their future paths. His experiment was an exploration of determinism, a philosophical concept that says that all future events are determined by causes in the past. The Aurora, a clockwork universe, showing the movement of the celestial bodies in the solar system, became a popular device after the publication of Newton's universal theory of gravity. Mechanical analysis. Laplace was inspired by classical mechanics, a field of mathematics describing the behavior of moving bodies, based on Isaac Newton's laws of motion. In a Newtonian universe, atoms follow the laws of motion and bounce around in a jumble of trajectories. Laplace's intellect would be capable of capturing and analyzing all of their movements. It would create a single formula that uses present movements to ascertain past and predict future ones. Laplace's theory had a startling philosophical consequence. It can only work if the universe follows a predictable mechanical path, so that everything from the spin of galaxies to the tiny atoms and nerve cells controlling thoughts could be mapped out into the future. This would mean that every aspect of a person's life up until their death has already been predetermined. They have no free will and no agency over their thoughts and deeds. Chance and statistics. Although mathematics helped to create such a crushing vision of reality, it also helped to dismiss it. By the 1850s, the study of heat and energy, thermodynamics, was ushering in a new model, the atomic world. To do this, it needed to describe the motion of atoms and molecules inside matter. Classical mechanics was not up to the task. Instead, physicists used a technique invented by Swiss mathematician Daniel Bernoulli in 1738, which used probability theory to model the movement of independent units within a space. Refined by Austrian physicist Ludwig Boltzmann, this technique became known as statistical mechanics. It described the atomic world in terms of random chance, something at odds with the mechanical determinism of Laplace's demon. By the 1920s, the idea of a probabilistic universe was solidified with the development of quantum physics, which has uncertainty at its heart. Pierre-Simon Laplace. Born into an aristocratic family in 1749, Laplace lived through the French Revolution and the Reign of Terror, in which many of his friends were killed. In 1799, he became Minister of the Interior under Napoleon Bonaparte, but was dismissed after only